This resource is the 8th in a series on derivatives. We will explain the concept behind derivatives and formally define them. We will discover how to find the derivatives of various forms of functions, including polynomials and trigonometric functions. We will consider how to differentiate products, quotients, and composition of functions. We will also consider applications for derivatives and how they relate to real-world situations. In the previous resource, one of the topics we discussed was higher-order derivatives, specifically the second derivative. In the real world, these derivatives are correlated to movement of objects. Consider some function f of t that describes the position of an object as a function of time. The derivative f prime of t for the function is the rate of change of the position. This is exactly the definition for velocity. The second derivative, f double prime of t, is the rate of change for the velocity, which is the acceleration for the object. Even higher order time derivatives also have specific names. The third derivative is called the jerk. The fourth is either called the jounce or the snap. The fifth is the crackle, and the sixth derivative is the pop. While these derivatives have fun names, they are not used often in actual application problems. Let's see an example. While this is not the most intelligent of things to do, the position of a .45 caliber bullet fired straight up in the air can be described by the function h of t equal to negative 16 t squared plus 832t plus 6. H of t describes the height of the bullet in feet after t seconds has elapsed from the firing of the weapon. Suppose we want to find out how fast the bullet is moving after 20 seconds, 26 seconds, and 40 seconds. We are also intrigued to find out the acceleration at each of those times. To find the velocity of the bullet, we need to consider the derivative of the position function. H prime of t equals negative 32t plus 832. To find the velocity at 20 seconds, we plug 20 in for t and solve. We find that the bullet is moving at 192 feet per second. Plugging 26 in for t, we find the velocity is 0 feet per second. This means that the bullet is at its maximum height, and 26 seconds is when the bullet changes direction. Plugging in, we find that the bullet's velocity is negative 448 feet per second at 40 seconds. Note that the velocity is negative. This is because the bullet is falling back to Earth, so its movement is in the negative direction. To find the acceleration of the bullet, we need to take the second derivative of the position function. When we do so, we get a constant acceleration of negative 32. This is very typical of real-world projectile problems, because the acceleration is due to gravity. But what other types of real-world problems would we use derivatives to solve? Suppose that Timothy Thompson, the owner of Timmy's Thingamabobs, can model the profit for selling n of his thingamabobs by the function p of n equal to negative 0.01n squared plus 60n minus 500. Timmy wants to determine how many thingamabobs he should sell to maximize his profits. To solve problems in which we want to find an optimal output level, we will use the following basic steps. First, find the derivative of the function we wish to optimize. Then we set that derivative equal to 0 and solve. We finish by calculating the second derivative to ensure that the value is appropriately the max or min. Now let's find Timmy's optimal output level. We had the profit function negative 0.01n squared plus 60n minus 500. We find that the derivative of this function is negative 0.02 n plus 60. We set negative 0.02 n plus 60 equal to 0. Adding the 0.02 n to both sides, then dividing, we find that n equals 3000. To check that this value is actually a maximum value, we take the second derivative. We get negative 0.02. Since the second derivative is negative, we have indeed found a maximum at 3000. So in order to maximize his profit, Timmy should produce and sell 3,000 thingamabobs. But what happens if there is no function clearly visible to optimize? Suppose Farmer Brown wants to build a dog pen on the longer side of his barn, which is 60 feet by 100 feet. He has 100 feet of fencing material with which to build the pen. Of course, he wants to give his dogs the most room possible in their pen. What should be the length and width of the dog pen? There is a basic process to completing applied maximum or minimum problems in which there is no clear function. First, we need to determine the quantity to be optimized. This quantity is usually clear from the problem description. Next, we need to find an algebraic expression for that quantity. Then we need to make algebraic adjustments so that we only have a function of one variable. After that, the process is identical to the process when we had an obvious function. Find the derivative of the function. Set the derivative equal to 0 and solve. Then find the second derivative and ensure we have correctly discovered a maximum or minimum. With the description of the problem, it is clear that we wish to maximize the area of the dog pen. Since we have a rectangular pen, this area is simply the length multiplied by the width. So our problem really starts with the third step. We need to find a method to describe the dimensions in a single variable. We choose to control the width of the pen. Since we have 100 feet of fencing, the length of the dog pen can be expressed as 100 minus twice the width. Therefore, the area, which is the length times the width, becomes the 100 minus twice the width multiplied by the width. This simplifies to 100w minus 2w squared. Taking the derivative with respect to the width, we get 100 minus 4w. We set that equal to 0. Solving, we find that the width should be 25. Taking the second derivative with respect to width, we get negative 4. We have indeed found a value that provides a maximum area. A length of 50 feet and width of 25 provides Farmer Brown a maximized area of 1,250 square feet in the pen for the dogs.